Cada segundo, en el mundo, se fabrican más de 2 millones de metros de alambre de cobre, pero solo una parte de él se convierte en una verdadera obra de arte de la ingeniería: las bobinas de inducción. El corazón de los transformadores, cargadores, motores eléctricos. En este video verás todo el camino, desde el brillante alambrón hasta la espira perfecta. Barniz, vacío, hornos infrarrojos. Todo para que el cobre soporte años de carga y no produzca ni una sola chispa. Quédense hasta el final. Se sorprenderán de cuánta maestría hay en un solo milímetro de alambre. El alambre de cobre para las bobinas de inducción generalmente no se fabrica en la misma planta donde se enrollan. Se suministra desde empresas especializadas que se dedican al trefilado, recocido y esmaltado. Todo comienza con el alambrón de cobre. Varillas de cobre gruesas, generalmente de 6 a 8 milímetros de diámetro, que se producen a partir de cobre electrolítico en plantas metalúrgicas. Luego, el alambrón se trefila a través de una serie de hileras cada vez más estrechas, reduciendo su diámetro. Después, el alambre pasa por un baño o una boquilla con barniz, que forma una fina capa aislante. A continuación, se seca en hornos especiales a una temperatura de 150 a 230 grados Celsius, capa por capa. Debe haber al menos 3 de estas capas. Y solo después, el alambre se transporta al lugar de fabricación de las bobinas de inducción. Las puertas se abren y un camión entra al territorio de la empresa. En su interior, pesadas bobinas de alambre de cobre, parecidas a carretes gigantes de hilo para titanes. Algunas del tamaño de una rueda de coche, con un peso de varios cientos de libras. Otras, más pequeñas, pero no menos importantes. Están cuidadosamente embaladas en cajas de plástico herméticas, cubiertas con una película protectora, con etiquetas por todo el perímetro. Un operario en una carretilla apiladora levanta con cuidado una bobina y la lleva a la zona de almacenamiento. Aquí todo es estéril. El suelo brilla en el aire. Un ligero olor a aceite de máquina y barniz. Cada bobina tiene su propio pasaporte, número de lote, diámetro del alambre, tipo de recubrimiento de barniz, fecha de esmaltado. El contenedor se abre solo justo antes de entrar en producción. Y entonces, es como desenrollar una cinta de oro. El alambre de color cobre brilla, perfectamente liso, con un finísimo recubrimiento de barniz que apenas se percibe a la luz. Un solo toque descuidado y se puede dañar el esmalte, por eso solo se toca con guantes. En la zona de trabajo hay máquinas de bobinado especiales. Parecen arañas silenciosas, listas para comenzar su minucioso tejido. El operador inserta la bobina de alambre en el soporte, pasa el extremo a través de un rodillo guía y lo fija en el núcleo de la futura bobina de inducción. Generalmente, un núcleo de ferrita o metálico. La máquina se pone en marcha. El alambre gira alrededor del núcleo con precisión micrométrica, vuelta tras vuelta, apretado, sin ningún espacio. La velocidad es controlada por una computadora. Demasiado rápido. El alambre podría romperse o sobrecalentarse. Demasiado lento. La producción sería ineficiente. Todo sucede en completo silencio. Solo se oye el ligero zumbido del motor y el susurro del metal. En la pantalla, el esquema de bobinado, tipo de bobina, número de vueltas, geometría, a veces incluso el ángulo de inclinación de las espiras. El operador vigila atentamente la tensión del alambre, porque hasta el más mínimo aflojamiento reduciría la inductancia y, por lo tanto, toda la bobina sería defectuosa. En un punto determinado, el alambre se detiene automáticamente, se corta con cuidado y el extremo libre se fija con un cierre especial o mediante soldadura. La bobina todavía está caliente por la fricción. Si es un bobinado multicapa, el proceso se repite, capa tras capa, con un fino aislamiento entre ellas. Al final, se obtiene un cilindro compacto, el corazón de cualquier transformador, cargador o motor eléctrico. En la nave se oye un ligero zumbido. Es la línea de impregnación que se pone en marcha. Las bobinas de cobre, recién ensambladas y aún tibias al tacto, avanzan por la cinta transportadora hacia la sección donde tendrá lugar su ritual de protección. Les espera un baño de brillante barniz dieléctrico o de resina epoxi transparente, sustancias que harán que cada vuelta sea fuerte, estable y resistente. Las bobinas pequeñas simplemente se sumergen por completo. Se hunden en el líquido, como una cuchara en la miel, y se dejan allí unos minutos. El barniz se infiltra lentamente entre las vueltas, envuelve el cobre, llena los huecos y literalmente pega la estructura en un todo único. Luego se retiran, levantándolas lentamente para que el exceso escurra sin dejar goteos. Pero para las bobinas más grandes, el ritual es más complejo, la impregnación al vacío. Las bobinas se sumergen en una cámara hermética y una bomba extrae el aire. El vacío saca las burbujas de aire no solo del espacio circundante, sino también de las microfisuras más pequeñas dentro del bobinado. Luego se introduce el barniz en la cámara y penetra en todos los lugares posibles, como el agua que inunda una grieta seca en una roca. Ni un microespacio queda sin cubrir. Todo esto no se hace por estética. Mañana mismo, estas bobinas trabajarán en condiciones difíciles, vibraciones, sobrecalentamientos, fluctuaciones electromagnéticas, y solo una impregnación fiable protegerá su forma y conductividad, para que ninguna chispa destruya lo que se creó con tanta precisión. Después de bañarse en barniz, las bobinas de inducción continúan su camino, hacia la zona de secado, un horno. Aquí no huele a panecillos, pero el ambiente es igual de atento. La temperatura, el tiempo y la precisión son críticamente importantes. Cada bobina entra en el horno, donde la temperatura sube hasta los 150 grados Celsius. Aquí, el barniz, que antes era líquido, comienza a polimerizarse. Minuto a minuto se endurece, convirtiéndose en una armadura fuerte y transparente. Un fino caparazón brillante que envuelve los alambres por todos lados. Es ligero, casi invisible, pero inquebrantable. La fijación de la forma es uno de los resultados principales de esta etapa. Mientras el alambre está blando, las vueltas pueden moverse un poco, especialmente durante el funcionamiento en un dispositivo con vibraciones o cargas de corriente. Pero después del horneado, todo se solidificará justo como debe ser. Algunas fábricas, en lugar de cámaras clásicas, utilizan hornos infrarrojos, que funcionan de manera localizada, calentando la superficie más rápida y uniformemente. Otras emplean sistemas de túnel, donde las bobinas se mueven en una cinta transportadora a través de un túnel de calor. Esto permite ahorrar energía y tiempo, especialmente en la producción en masa. Y otro punto importante, la mejora del aislamiento. Después de endurecerse, el barniz se vuelve resistente a la humedad, al sobrecalentamiento, al impacto mecánico e incluso a algunos productos químicos. Esto significa que cada bobina que salga del horno podrá funcionar durante años y no perder ni una pizca de su fuerza. Después del horneado, los bordes de las bobinas pueden quedar un poco irregulares. Sobresalen restos de barniz, recortes de alambre o exceso de material. Todo esto se recorta o lija cuidadosamente, utilizando equipos de precisión, discos abrasivos, microrectificadoras, a veces incluso corte por láser. Esto es especialmente importante para las bobinas que deben encajar perfectamente en ensamblajes donde cada milímetro cuenta. Después de la impregnación y el tratamiento térmico, el barniz o la resina epoxi a veces sobresalen en forma de gotas o pequeños excesos. Se eliminan delicadamente a mano o con equipos especiales. A veces se utilizan cuchillos ultrasónicos o microfresadoras para preservar la estructura, pero eliminar lo superfluo. La forma final debe ser perfecta para el montaje. Altura correcta, anchura, ubicación de los terminales. El producto se verifica para asegurar que cumple con las especificaciones técnicas, visualmente, mecánicamente y a veces con escáneres tridimensionales. Porque si una sola vuelta está ligeramente desplazada, eso ya puede ser motivo de rechazo. Every year, over 2 million tons of welding wire are produced worldwide, and each spool starts with a rigorous casting process that forgives no mistakes. The steel here is analyzed down to the 10,000ths, and the pressure on the wire during drawing reaches up to 20 tons per square inch. This isn't just wire, it's the backbone of industry. From National Aeronautics and Space Administration rockets to bridges over the Mississippi River. In this video, we'll show you how a dirty rod is transformed into a perfect, shiny thread that has passed through acid, flame, and copper. This is a choreography of precision that keeps the world of welding afloat. Watch till the end. It's going to be spectacular. In the very heart of America's steel regions, where the air still smells of oil, metal, and old tools, the birth of welding wire begins. Not every steel can withstand this trial. Almost suitable raw material doesn't pass here. Only the best, tested, and verified down to 1/1000%. For carbon wire, they look for steels with a precise carbon content, so the weld is strong but not brittle. For stainless steel, chromium, nickel, and molybdenum come into play. And for specialized applications, say in aviation or nuclear energy, they choose alloy steels, where every gram is calculated with an accuracy of 1/10,000%. A large portion of the steel arrives at the factories in the form of hot-rolled coils or ingots. One such coil can weigh from 5 to 15 short tons. And before the steel becomes wire, it's analyzed at a chemical level. The content of carbon, sulfur, phosphorus, silicon, manganese, nickel, everything must meet the strict standards of the American Welding Society. An alloy that is off by even 0.02%, and the entire batch goes for remelting or another purpose. All analyses are conducted in laboratories right on the factory grounds, using spectrometers and X-ray analyzers. In industrial centers like Ohio, Pennsylvania, or Illinois, such factories operate 24/7, and every batch of steel that enters the drawing shop has its own biography, melt number, place of origin, grade, percentage of impurities, cooling method after rolling. All of this is recorded in digital systems that are synchronized with the production lines. American manufacturers, especially those supplying welding wire for the National Aeronautics and Space Administration, Tesla, Boeing, or military facilities, pay huge attention to certification. Next comes the drawing process. And this isn't just a routine stage in wire production. It's an ancient craft that dates back to antiquity, when masters drew gold and silver threads for jewelry. In medieval Europe, the first mechanisms for drawing iron appeared. Wooden structures with a manual drive and a hole through which the metal was pulled. The first documents about drawing shops date back to the 15th century in Nuremberg. And during the Industrial Revolution, this process gained incredible momentum. Now steel was drawn not for decoration, but for construction, telegraphs, and industry. Today, in American factories, drawing is a choreography of high-precision technology. Steel rods, less than an inch thick, are stored in coils or as straight bars. Before drawing begins, they are cleaned. Picture a hot steel rod, fresh from the rolling mill. Its surface is dark gray, covered with a hard, brittle crust. That scale, a mixture of iron oxides that forms when the metal comes into contact with air at high temperatures. If it's not removed, the wire will be rough and have defects. And that means a bad weld seam, problems with feeding in an automatic machine, extra sparks. Steel rods are lowered into baths with an acid solution. It's like a bathhouse for the metal. the acid eats away the scale, leaving a shiny, clean surface. After this, the rods are thoroughly rinsed with water and dried. Otherwise, the remaining acid will cause corrosion. Mechanical cleaning happens like this. In a closed chamber, a powerful compressor shoots a stream of metal balls or abrasive sand directly at the rods moving on a conveyor. It's like sanding with a hurricane. The scale is literally blasted off the surface, and the rod itself acquires an even, matte appearance. This method is effective when it's important to avoid chemical contamination, for example, in the food or oil industry. After cleaning, the steel rod looks perfect. But to pass through dozens of holes under pressure of tens of tons, it needs protection. The rods are dipped into baths with dry powdered lubricants, for example, based on calcium or sodium soap, or they are coated with liquid emulsions. Sometimes, lubricants are applied as a film that then polymerizes in a special furnace. This creates a slippery shell that reduces friction, dissipates heat, and extends the life of the drawing tools. Then the drawing process itself begins. The rod is pulled through a series of cone-shaped holes that gradually reduce the wire's diameter. Imagine, the pressure reaches tens of thousands of pounds per square inch, and the speed up to 3,000 feet per minute. In some cases, the wire passes through 8 or 12 such holes, and each one is a microscopic test of strength, flexibility, and precision. For welding wire, the key moment is diameter control. A deviation of even 1/10,000th of an inch, and the wire might not feed automatically into the welding machine or could cause an unstable arc. On modern lines, diameter control is done in real time. Laser sensors scan the wire as it passes through the machine tunnel, instantly reacting to any deviations. Drawing is like rolling out dough, but with micron-level precision, industrial fury, and a steel temperament. And all this so that every weld seam, from a farmer's tractor to a missile silo, holds strong. The wire that has just passed through dozens of drawing machine holes, although thinned to a perfect diameter, remains stressed on the inside. Microscopic cracks, residual stiffness, hidden internal friction. All these are potential enemies of a quality weld seam. To release this stress, the wire undergoes a thermal soul cleansing, annealing. This is the process of heating the wire to a temperature of approximately 1,300 degrees Fahrenheit and then slowly cooling it. Picture a huge furnace as long as a subway car. Inside, rows of steel wire, wound on drums or passing continuously like a shiny snake. The temperature inside is such that the metal glows a cherry red color. At this moment, all the internal stresses that arose during drawing begin to dissolve. Atoms that were crumpled into knots like compressed springs return to their places. The wire seems to exhale and becomes alive, flexible, obedient. The process can last from 30 minutes to several hours, depending on the wire's thickness and material. Cooling occurs gradually, often in a controlled environment to prevent the formation of scale or rust. There are also continuous annealing lines, where wire moving at speeds of tens of feet per minute passes through a heating zone, and then through a cooling zone. This speeds up production, but requires perfect synchronization. The result? A wire that just an hour ago could have snapped at the slightest bend is now ready for work in the most difficult conditions. It's soft, pliable, yet retains its strength. During welding, it doesn't spatter, doesn't jam in the mechanism, and doesn't create excess stress in the seam. Or after annealing, the wire becomes flexible and strong, but still not ready for its main mission. It has one drawback. Steel, although reliable, is not a perfect conductor of electricity and is too vulnerable to corrosion. Now imagine, it goes into a welding machine where a spool rotates, the feed is continuous, and at the end of the wire, an arc that heats the metal to thousands of degrees. In such conditions, additional armor is needed, thin, almost invisible, but extremely important. This is a copper coating. Copper conducts electric current 6 times better than steel. A thin layer ensures fast and stable current transfer from the contact tip to the arc. This guarantees uniformity of welding and less spatter. Steel, especially in a humid or aggressive environment, rusts. But copper doesn't. Even with long-term storage or transport, copper-coated wire won't get covered in a rusty film that would spoil the feed or electrical contact. The copper coating reduces friction between the wire and the feed rollers in the machine. This means less wear on the mechanics, less frequent maintenance, and a longer service life for the equipment. And the welder is less stressed. The feed is smooth, without jerks. The wire passes through a bath with a copper sulfate solution. Under the influence of an electric current, copper deposits on the wire's surface, evenly, densely, without voids. This is a method that requires precise control of temperature, voltage, and exposure time. In large workshops, this is a conveyor. The wire goes from the spool into the bath, and then through a dryer. Every hour worldwide, over 1,000 tons of copper are smelted, the metal that forms the foundation of civilization. It travels a path through thousands of degrees to become a simple rod. But behind this humble form lies an explosion of temperatures, fire, and precision down to the micron. Here, furnaces melt bronze at 1,910 degrees Fahrenheit. Here, metal is processed, ground, stretched until it becomes perfect. All under the watchful eye of engineers, sensors, and fire. Today, you will see how the heart of technology is created, and it is spectacular. Every day around the world, metal that has traveled thousands of miles goes into furnaces and crucibles to become a rod, humble but indispensable. And it all begins with a copper heart, cathodes, ingots, and scrap. A copper ingot, heavy like a large suitcase. It blocks light and rings if you hit it. It weighs about 100 pounds, and its journey is just beginning. And here's a cathode, a plate the size of a door, up to 300 pounds, refined by electrolysis, almost pure copper. Its color is warm, deep, like the autumn sun at sunset. These giants, as well as fragments of old pipes, parts, and wires, all of this is dumped into the deep bunkers of the melting shop. For brass, zinc is added to copper. The soft red metal suddenly becomes golden, hard, and elastic. In classic recipes, 60% is copper and 40% is zinc, although the proportions can be adjusted. And if bronze is needed, copper is combined with tin, sometimes with aluminum, silicon, or phosphorus. Bronze is less flexible but more resistant. It was bronze that gave its name to an entire era, the Bronze Age. The classic formula is 88% copper, 12% tin. These numbers are not accidental. It's a precise balance. A little more, and the metal will be brittle. A little less, and it won't withstand any stressed structure. Everything that has just been gathered, copper cathodes, ingots, zinc bars, tin granules, is loaded into furnaces that know no mercy. These are either induction furnaces, where the metal is heated by an electromagnetic field, or gas-fired crucibles, where the flame can be heard even through thick walls. The temperatures here are hellish. Brass melts at 1,700 degrees Fahrenheit. Bronze requires even more, up to 1,910 degrees. The metal in liquid state, shining, heavy. It cannot be touched, only observed through special glasses. One careless movement, and half a ton of molten alloy can spill onto everything around. At this moment, fluxes are added to the melt, powders that help collect slag, meaning impurities, oxides, remnants of old metal. They float to the surface, forming foam or a crust, which is carefully removed. One melting crucible holds up to 10,000 pounds of metal. The temperature inside is controlled by thermocouples capable of withstanding 2,000 degrees Fahrenheit and more. In nearby laboratories, samples are constantly taken. It's like with winemakers. They check the chemical composition, test hardness, and prepare analytical charts. The metal hasn't become a rod yet, but it already has its passport. Metallurgists in protective suits, with masks on their faces and heat-resistant gloves, approach the furnace. On their faces is calm concentration. They are used to working near metal hotter than lava. All movements are honed, like in a dance where the price of a mistake is higher than anything else. The furnace tilts, or the bottom gate opens, and a stream of molten alloy erupts from its depths. It's bright yellow, as if the sun itself decided to turn liquid. The stream is directed into casting molds, special steel or graphite forms. They come in different shapes: square, round, hexagonal. Depending on what the future rod will be, the molds are already heated. If they are cold, the metal might kick back, splash, or crack. The temperature in them is above 500 degrees Fahrenheit, but this is minor for the world of metal. At the moment of pouring, the workshop falls silent. Everyone watches to see if it's flowing correctly, if no slag is getting in, if no air pockets are forming. Sometimes steam erupts from the mold. That's water left after the previous cooling. Steam hisses, mixes with the heat, smells of metal and earth. In foundry production, molds, especially temporary ones, can be made of a sand-clay mixture reinforced with resins. When molten metal is poured into such molds, they char, burn, or evaporate moisture, and this gives off a smell similar to damp earth, ash, minerals after rain. Or before pouring, the molds might contain remnants of water or condensation. And when thousands of degrees suddenly hit a drop, steam with a mineral aroma is created. It smells like earth after a thunderstorm. The same effect, but in the workshop. It's hard to breathe in the workshop. Heat, dust, hot air rising, and underfoot. Layers of cooled bronze, brass, fine scrap. The floor glitters. Particles of alloy that didn't make it into the mold solidify immediately, forming a shiny crust. The molds fill up quickly, and the metal begins to cool. Slowly at first, then faster. Before your eyes, the magic of solidification. The molten river becomes a solid body. Bronze, a deep brown. Brass, yellow with a sheen, like fresh gold. When the metal starts to set, workers take long metal rods and smooth the surface, remove residual slag, and check the edges. Some laugh, joke, but keep one eye on the melt anyway. Here, it's important not to miss anything. After a few minutes, the molds are cooled with water or air. The rods are pushed or pulled out of the molds, still warm but already solid. They are steaming, hissing, as if surprised themselves that they have become a single body. As soon as the rods are removed from the molds, the next phase begins: processing. Hot, heavy, still smelling of metallic smoke, they head further into the hands of machines. First, cooling. If this isn't done, the alloy will continue to crystallize unevenly and cracks may appear. The rods are doused with streams of water or submerged in large baths. Water hisses, steam rises in a wall, the air becomes heavy and humid. The metal darkens but becomes harder. After this, they are directed to the cutting line. Each rod must have a precise length, say 10 feet. Robots trim the ends, uneven, melted, with excess material. The cut looks like a shiny mirror, from which crumbs of hot metal are dripping. The operator checks if the ends are even, if there are no voids visible inside. Next, rolling. This is one of the most impressive parts. The rods are passed through a system of rolls, huge metal cylinders rotating with a roar. This is where the precise diameter is formed. Whether it will be 5/8 of an inch or 3/4 depends on the order. The metal becomes thinner, longer, and more uniform. It's as if it's being drawn out before your eyes. At this point, pressure and temperature sensors are working, because even a rod overheated by a few degrees can warp or disrupt the structure. In the next stage, straightening. After rolling, the rods may still have minor bends. They are placed on a line with rotating rollers, where special hydraulic presses or automatic hammers straighten them to millimeter precision. After mechanical processing, surface finishing, the rods are ground or machined to remove scale, minor irregularities, microscopic inclusions. When they pass through polishing machines, it seems as if the metal comes alive. It starts to gleam, like a freshly polished brass pipe in a parade. And finally, checking the dimensions. Here, precision is like in surgery: calipers, laser scanners, digital gauges. one extra micron, and the whole batch can be rejected. When the rods already look perfect, the moment of truth arrives: calibration and testing. Each sample is checked for compliance with precise technical parameters. Laboratory technicians and engineers take over. They test the diameter, length, weight, hardness, flexibility, and even the microstructure of the metal. The rod is fed into calibrating machines with high-precision optics or lasers. They detect even slight deviations within fractions of a millimeter. Then a sample is taken from it for tensile testing. The metal is stretched to its limit until it breaks. This shows how much load the rod will withstand in real conditions. Another test: bending. It is clamped in special pliers and bent to a certain angle, checking whether cracks appear. Everything is recorded. If the rod fails, it is either remelted or scrapped. Only those that have passed the full cycle receive marking and move on. After testing, the rods are marked, packaged, and sent to warehouses or directly to customers. Some are wrapped in protective film, others stacked in wooden boxes or metal racks. They are sent to workshops where they will be manufactured into parts for technology, construction, and electronics. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is viaje, stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining crudelties, precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is Kardblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Every year, the world produces over 60 million metric tons of aluminum, and a significant portion of this metal is turned into key parts for automotive engines. Did you know that over 75% of modern engines have aluminum cylinder heads? This choice isn't accidental. Lightness, strength, and the ability to withstand high temperatures make aluminum an ideal material. But what happens behind the scenes in the production of these critical components? How are tons of metal transformed into complex, high-precision parts? Today, we're diving into the fascinating world of industrial manufacturing, and we'll show you the whole journey, from raw material to finished cylinder head. Cylinder heads are most often made from two primary types of materials: aluminum alloys and cast iron. As of 2025, over 75% of modern automotive engines are equipped with aluminum heads, due to their lightness, good thermal conductivity, and the reduction of the overall weight of the power unit. One aluminum cylinder head assembly weighs on average between 10 and 20 pounds, whereas cast iron equivalents can exceed 40 pounds. Aluminum for such parts isn't just metal, it's a high-quality alloy, for instance with added magnesium or copper, which provides strength at high temperatures. The main suppliers of aluminum are countries like the People's Republic of China, which provides over 60 million metric tons annually, and India. In the United States, the majority of aluminum raw material is supplied by sea transport in the form of ingots or granules, which are subsequently remelted at local foundries. One standard 20-foot container holds up to 48,000 pounds of aluminum ingots, which is enough to produce over 1,000 heads. Cast iron, although less popular in new engines, is still actively used in heavy machinery and trucks due to its durability. Its production requires components: iron ore, coke, and limestone. The United States partially extracts ore itself, but imports a significant portion from Canada and Brazil. Rail transport is used. One typical train with raw materials can deliver 10 to 15,000 tons of iron ore to metallurgical plants. After the materials arrive at the facility, they undergo cleaning, sorting, and melting. For example, casting one cylinder head requires up to 22 pounds of aluminum, and the cycle from melting to cooling takes about 90 minutes. This is just the beginning of the production chain, in which each part goes through dozens of stages before being assembled onto an engine. Aluminum ingots or granules arrive at the plant in sealed containers. They are unloaded onto special platforms with automated cranes and delivered to the melting shop. Before melting, the aluminum is cleaned of impurities and moisture to avoid porosity in the finished casting. For this, the raw material is placed on vibrating tables with metal detectors or sorting conveyors. Robots or operators manually or mechanically reject unsuitable material. This is how contaminants, paint, oil, plastic, and shavings of other metals are identified. Thanks to quality cleaning of aluminum before melting, the rejection rate is reduced by 60 to 80%. The storage temperature for the raw material is controlled, about 70 degrees Fahrenheit, to avoid condensation, which can cause microbubble explosions if it gets into the molten metal. After cleaning from moisture and impurities, the aluminum is fed into large melting furnaces. These can be gas or induction units that heat the metal to approximately 1,220 degrees Fahrenheit. A stable melting temperature is maintained in these furnaces thanks to automated control systems, which prevents overheating and preserves the homogeneity of the future alloy. Furnaces typically have a volume of 5 to 10 tons, and one such furnace can produce up to 300 or even 500 cast cylinder heads per shift. One shift lasts 8 or 12 hours. The production flow is set up so that the molten metal is continuously supplied for casting, so even 15 or 20 minutes of downtime can cost the enterprise thousands of dollars due to lost pace and cooling of the material. Alloying elements are added to the molten aluminum, primarily silicon and magnesium. These elements increase the strength, heat resistance, and wear resistance of the finished part, making it suitable for operation under high pressure and fluctuating temperatures in the engine. As you can see, magnesium doesn't just improve human strength and wear resistance, but aluminum's too. After adding impurities, the alloy necessarily passes through a ceramic filtration system. Special porous filters capture oxides, microscopic particles of slag, and residual impurities. Without this filter, slag could get into the mold, form microcavities in the part's structure, and reduce its lifespan by tenfold. Filtration usually occurs in the ladle or holding furnace, where the molten metal is transferred from the main furnace. This is an intermediate stage where the metal is again stabilized by temperature and checked for chemical composition using spectrometers to precisely match tolerances. After cleaning and filtration, the molten aluminum goes to the casting shop, where it is poured into molds, a key moment when hot metal turns into a specific part, the cylinder head. This process must be extremely precise because the mold is complex, with numerous channels and cavities, and the engine's performance depends on the casting quality. Most often, gravity die casting or high-pressure die casting are used for head production. In the first case, the molten metal flows by gravity into a metal mold that can withstand several thousand cycles. In the second, the molten metal is injected under pressure up to 10,000 psi, ensuring precise filling of even the smallest channels. The mold, made of high alloy steel, is preheated to 400 degrees Fahrenheit or more to avoid thermal shock. The metal is supplied from a ladle or through an automated continuous feeding channel. A venting and gating system ensures air displacement, otherwise voids will form. The metal cools in the mold for 30 seconds to 1.5 minutes, after which the mold opens and the casting is sent on for further processing. Modern lines are equipped with sensors for temperature, pressure, and filling. The control system monitors the volume of molten metal, feeding speed, mold temperature, and metal temperature in real time. A deviation of more than 2%, and the machine automatically rejects the blank or adjusts the parameters. One casting station produces 40 or 60 heads per hour, depending on the technology. After the casting and cooling of the metal are completed, the next stage begins, removing the head from the mold. If sand casting was used, the mold is broken. It's a single-use structure made of a sand-clay mixture, so it's simply broken apart to get the casting. In the case of die casting, a metal mold is used, which automatically opens, and the part is ejected by special pushers. At this stage, the so-called gray or rough blank is obtained, an unprocessed head with gates, risers, and irregularities. Its weight is 10 to 20 pounds, depending on the engine type and design. Almost immediately after removal, the heads are often sent for heat treatment. This typically includes quenching and tempering. The process involves heating to 1000 degrees Fahrenheit, holding at that temperature, and controlled cooling. This strengthens the metal structure, increases hardness, wear resistance, and thermal stability, critical parameters for operation in the engine's hot zone. After heat treatment, the cylinder head proceeds to the computer numerical control machining stage. The head is secured on a fixture in a multi-axis machining center. A computer program precisely sets the coordinates, speed, and order of processing. Machining includes milling the mating surface to the engine block, drilling holes for bolts and other parts, boring channels for coolant and oil, forming valve seats and guides. One machining center can complete a full cycle in 10 or 25 minutes. Every hour worldwide, people eat over 500 tons of popcorn. That's more than the weight of 2 Boeing 747 jets. But have you ever stopped to think that inside every single kernel, there's a miniature steam boiler that explodes with enough power to increase its size by 50 times? It all begins in ancient caves in Mexico and ends up in ultra-modern factories where hot air waves, optical sorters, and cheese powder sprayers create that perfect crunch you love. Ready to see how a simple corn kernel turns into the explosive taste of your childhood? Then don't blink. It's about to get even tastier. Popcorn is one of the oldest snacks in the world. Archaeologists have found corn kernels that could still pop in caves in Mexico and Peru, and they're over 5,000 years old. And here's a cool fact. Some of those old kernels were actually still capable of turning into popcorn in a microwave today. Can you imagine that? The first people to start eating popcorn were Native American tribes, like the Maya, Aztecs, and Incas. For them, it wasn't just a treat. Popcorn had ritual significance. They used it in ceremonies, decorated idols with it, and even made jewelry and necklaces from it. Popcorn was kind of like a gift for the spirits. Popcorn made its way to North America thanks to the local tribes, and they were the ones who introduced the early settlers to this wonder. There's a legend that at the very first Thanksgiving in 1621, popcorn was also on the table. But it wasn't until the 19th century that popcorn really started becoming popular among Americans. People used to pop it right in skillets over a fire, and then, boom! In 1885, the first street vending machine for making popcorn appeared, created by Charles Cretors. And that was it. Popcorn went out into the world. First to fairs, then to movie theaters. The Great Depression really brought popcorn its fame. It was cheap, tasty, and fun. A little bit of comfort during tough times. That's why it's still associated with coziness, entertainment, and childhood today. Popcorn isn't just regular corn. It's a special variety, Zea mesa verta, the only one that can explode when heated. And it all starts in the field. Popcorn corn kernels are planted in the spring when the soil has warmed up enough, usually at a temperature of at least 50 degrees Fahrenheit. Fields are often chosen in drier regions because popcorn doesn't like too much moisture, which can spoil the kernel. In the United States, the main farms are located in the states of Indiana, Illinois, Nebraska, and Iowa. The plants grow slower than regular corn, but the result is worth it. It's important to wait for the cobs to fully mature. The kernels need to be hard, with low moisture content, so they pop well when heated. After harvesting, the cobs are dried, first naturally and then in special dryers, where the moisture level is brought down to an ideal 13 or 14%. Next, the cobs are shelled. The kernels are separated from the cobs using special machines. Then, the kernels go through a sorting system. Only whole kernels, uniform in size, are selected because the quality of the pop depends on this. After sorting, the kernels are packed into bags or containers and sent to factories or processing centers, where they'll be turned into the familiar popcorn we all know. Salty, sweet, caramel flavored, or even with cheese. After harvesting, drying, and sorting, the corn kernels are transported to specialized facilities. A typical popcorn plant in the United States processes up to 500,000 pounds of kernels per week. The biggest players in the market, Conagra, Pop Secret, Act 2, have their own supply networks and completely control the process from the field to the package. The kernels arrive at the factory in trucks, carrying up to 50,000 pounds of corn at a time. The truck dumps the kernels into a receiving pit where they move along a conveyor belt to the cleaning and inspection line. A sample is taken from the batch and placed in a laboratory moisture meter. The ideal moisture level is about 14%. If it's higher or lower, the batch won't proceed, or it's sent for drying. To check the physical quality of the corn, a sample of kernels is placed in an optical sorter. It scans each kernel with cameras under bright light, and it automatically rejects kernels that are chipped, have dark spots, fungus, or a different color. Also, an operator can manually check the percentage of debris, stones, hulls, and insect-damaged kernels. According to US standards, no more than 2% defective kernels per batch. It's mandatory to check how many kernels pop during a test heating. A good variety yields a minimum of 98% popping. After all checks, the kernels are cleaned, polished, and calibrated. They are often treated with special food additives or oils that improve texture, flavor, and shelf life. Popcorn comes in two main types: kernels for microwave or popcorn machines, and already popped, flavored, and packaged popcorn. The kernels are poured into heated drums, huge steel cylinders that rotate with a dull thud. Inside is dry air, heated to 450 degrees Fahrenheit. That's a temperature at which steel darkens and paper ignites in seconds. Hundreds of thousands of corn kernels continuously rotate, heating up from all sides. Inside each kernel, moisture gradually turns into steam, but it can't escape. The hard outer shell, which withstands incredible pressure, keeps it locked in like a miniature boiler. The tension builds, and then pop, pop, pop. The kernels burst with a characteristic sound that can be heard even through the drum casing. It's like fireworks, but instead of sparks, fluffy white popcorn snow that quickly fills the chamber. The moment a corn kernel explodes, its size increases by 40 or 50 times. It's literally a transformation, from a hard, shiny ball to a light, porous flour that immediately starts smelling like childhood, movie theaters, and salt. Everything happens in a flash. Each batch is ready in 2 minutes, and the drums work non-stop. The machine spits out hundreds of liters of hot popcorn, which immediately heads onto the flavoring stage. And this entire explosive performance is under complete control. Because what's at stake isn't just kernels, it's your perfect crunch. As soon as the corn clouds have popped in the drums, the next stage begins, creating that unforgettable flavor. Without it, popcorn is just crispy foam. With it, it's a caramel temptation, a cheesy sin, or a salty masterpiece. And it all happens on precise, computerized flavoring lines. A hot conveyor belt carries the popcorn to special coating drums where it gets its character. These drums are large, rotating cylinders with spray nozzles inside. Here, the popcorn tumbles around like on a carousel, and mixtures of salt, butter, caramel, or cheese powder are evenly sprayed under precise control of temperature and humidity. Popcorn arrives from the poppers or caramelizers hot. The temperature can reach 300 degrees Fahrenheit. To prevent kernels from sticking together and ensure crispness, the product is immediately sent onto conveyor belts or screens that are ventilated with cold air. The flow of cooling air is controlled by a computer that adjusts the temperature and speed according to the volume and type of popcorn. This allows a large batch of 500 or 1,000 pounds to cool down in 5 minutes without compromising its structure. When the popcorn reaches a temperature of about 77 degrees Fahrenheit, it is sent to automated packaging lines. It first passes through a sorting drum, where unpopped kernels and broken pieces are screened out. Only perfectly popped, light and airy kernels make it into the packaging machines. Depending on the product type, popcorn is packed into polypropylene or metallized bags, cardboard boxes, or large bags for bulk sale. Before sealing, an inert gas, usually nitrogen, is injected into the bags. This displaces oxygen, which slows down fat oxidation and extends shelf life up to 9 months without loss of quality. Then the packaging is hermetically sealed and marking is applied: manufacturing date, batch number, flavor, and ingredients. On average, one line can package 80 to 150 bags per minute, depending on size and weight. Cooled and packaged popcorn goes to palletizing and storage, or directly to distribution, to stores, movie theaters, or for online orders. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? And that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this: in every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense, solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire. So the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation.